In chapter 6, we will look into discrete random variables. Discrete random variables have outcomes that take on whole numbers when an experiment is conducted. A discrete probability distribution meets the following conditions. Each outcome in the distribution needs to be mutually exclusive. The probability of each outcome must be obviously between 0 and 1. The sum of probabilities for all outcomes in the distribution need to add up to 1. Now, when we calculate the mean of a discrete probability distribution, we need to take into account that it's a weighted average of the outcomes of random variables in the distribution. The expected value is the same, it's another term used for the mean, for the average, so do not get confused when you are asked to calculate the expected value. It's the same thing as your average. The formula now, when we calculate the expected value, the mean, E of x, mu, is equal to the sum of x times P of x. That means you take the outcome times its corresponding probability for each one, and then at the end you add them. This is how you find the average, once again, for a discrete probability distribution. The variance measures how spread out the results of an experiment are from one trial to the next one. The formula for the variance for a discrete, once again, probability distribution is sigma square is equal to the sum of the square deviation of every entry from the mean times its corresponding probability. The standard deviation, as always, is the square root of your variance. So whatever you get for the variance, you simply take the square root of that, and this will give you the standard deviation. In order to calculate the mean, the variance, and the standard deviation, it is best to use a table where you have all outcomes alongside the corresponding probabilities. If I'm not giving you the corresponding probabilities, I will be giving you the frequencies, and based on the frequencies, you will be able to use the relative frequency, which is the probability. You will take the product of each one, you will add them, this will give you your mu, and then you will use it for your variance. The summation of this column will give you the variance, the summation of this column will give you the average. Be very, very careful when you calculate your average. You don't want to make a mistake in the average, because if you make a mistake in the average, your variance will be wrong and your standard deviation therefore will also be wrong. Let's look at an example. Calculate the mean, variance, and standard deviation for the following distribution. This is a typical example where I'm giving you all possible outcomes alongside the corresponding probabilities. You create your table where you take the product of the first two columns. So you do x times P of x, 0 times 0.3, 1 times 0.2, 2 times 0.2, 3 times 0.3. Whatever you get, at the end, you add them, and this will give you your expected value, your mu. So your average in this case is 1.5. Your average is 1.5. Now, once you have your average, you move on to calculating your variance. And to calculate the variance, you first take the square deviation of every outcome from the mean. So 0 minus 1.5 square, 1 minus 1.5 square. And then you calculate it with the corresponding probability that you have here. Whatever you find, at the end, you add them all, and this will be your variance, your sigma square. Once you have your sigma square, which in this case is 1.675, you take the square root of that, and this will give you your standard deviation. Now, a binomial experiment has the following characteristics. The experiment consists of a fixed number of trials denoted by n. Each trial has only two possible outcomes, a success or a failure. The probability of success and the probability of failure are constant throughout the experiment, and each trial is independent of any other trials in the experiment. Now, The number of successes in a binomial experiment must range from 0 to n. The formula for the binomial distribution is the following. So if we were to use the formula for a specific binomial probability, we would need to do n factorial over n minus x factorial times x factorial, and whatever we got from here, we would multiply it with p raised to the power of x times q raised to the power of n minus x. So let's look at some symbols. First of all, factorial. When we talk about factorial, we need to know what it means. So for example, if n was 3 and you had to calculate 3 factorial, you would do 3 times 2 times 1. If n was 5 and you had to calculate 5 factorial, you would do 5 times 4 times 3 times 2 times 1. P is the probability of success. This probability will be given to all the problems that you will encounter as far as binomial probability is concerned. Q is the probability of failure. As we mentioned before, we have two possible outcomes, success and failure. If the probability of success is given, you can automatically find the probability of failure, Q, by subtracting the probability of success from 1. So x is the number of successes, n is the number of trials, your sample size, p is the probability of success, q is the probability of failure, which you always find by taking 1 minus p. P plus q will always have to add up to 1. P plus q always add up to 1. Now, the mean of the binomial distribution represents the long-term average number of successes to expected based on the number of trials. The formula for the mean of the binomial distribution. So if we're looking for the expected value for binomial probability distribution, all you really need to do is multiply n times p. N will always be given, p will always be given. So you simply multiply the two. The standard deviation of the binomial distribution represents the variation we would see in the number of successes over n trials, assuming the chance of successes is p. These are the formulas for variance and standard deviation. They're pretty straightforward. The variance is n times p times q. We find q once again by doing 1 minus p. And of course, for the standard deviation, we simply take the square root of the variance. Now, if we were to use our graphing calculator to calculate the binomial probability distribution, instead of using this formula, you can use your graphing calculator to do your calculations a lot faster. So if based on whatever calculator you have, you would go to second, vars, variables, and you would scroll down to binomial PDF, and this is where you would enter your information, n, p, x, n, p, x. The comma is right here on top of 7, n, p, x. And you have all the directions here. Now, let's look at this example. The probability to pass Math 151 is 0.8. A sample of 50 students is given. What is the probability that 4 students will pass the course? So you are given the probability and you are given the sample size. P is equal to 0.8, N is equal to 5. You are looking for the probability that 4 students will pass the course. So you're looking for the probability of X to be equal to 4, which is perfect because you don't need to rewrite anything. You have X equal to a specific value. All you need to do is plug in the information. If you were to use your formula, this would be n factorial, which is 5. So 5 factorial over 5 minus 4 factorial times 4 factorial times 0.8, which is your p, raised to the power of 4, because this is your x, times 0.2, which is q, raised to the power of n minus x, 5 minus 4. So if you were to do the calculations, you would end up with 0.4096. Now, if we were to use our graphing calculator, we would do binomial PDF 5, comma, 5, comma, 0.8, comma, 4, close parentheses, and enter. 0.4096, which is a lot faster than the formula, for sure. For the same problem, what is the probability that at least 4 students will pass the course? And this is where I want you to be very, very careful to keywords. At least means what? You're looking for the probability of x to be greater or equal to 4. Since you have a discrete probability distribution, you have to express this in a format where x is equal to a specific value. At least, greater or equal to 4. Greater or equal to 4 means what? Your probability of x to be equal to 4, plus the probability of x to be equal to 5, and you stop there. Why do we stop there? Because you can only go up to the sample size. Your sample size is 5, so you go up to the sample size. And if you were to use your graphing calculator, you would do binomial PDF 5, 0.8, 4, plus binomial PDF. N and P do not change. The only thing that changes is your X. And you add them, you can do it all at once, 0.7373 for the probability. So if we were to use our graphing calculator, we would do, let me just, second vars, once again, binomial PDF, enter, we have 5, 0.8, 4, close parentheses, plus second vars, binomial PDF, 5, 0.8, x now is 5, close parentheses, and enter, 0.7373. If we wanted to use, now if we wanted to find the expected value, the variance, and the standard deviation for the binomial distribution in the same example, all we would need to do is multiply n times p, 5 times 0.8, which is 4. This would be your average. Variance n times p times q, which means 5 times 0.8 times 0.2, 1 minus 0.8, which is 0.2. This would be 0.8. And then you take the square root of 0.8 to find your standard deviation, which is 0.8944. Also, make sure that you always review the objectives and the formulas that are given in your notes. That will help you immensely, especially as far as the formulas are concerned for each chapter. So this concludes the notes for chapter 6.